Hello friends, welcome to this lecture. In this lecture we would be covering the introduction to the linear regression. So what is a linear regression? A linear regression is a statistical approach to model the relationship between the dependent variable y and one or more independent variable. So now let's consider the equation y is equal to mx plus c, where y is your target variable, m is the slope, or we call it the weight, and x is your feature and c is your bias. So purpose of the linear regression equation is to make the prediction for the target variable. Okay, so let's look at this particular picture over here, which gives us illustration of regression line for one or more independent variable. So if you see this particular red line is dividing the quadrant into two half, so we get certain pixels in the blue color, which are above the red line, and some of them are below the red line. Any pixel that's falling on the or the dot that's falling on the red line, it's basically a prediction. That's how the linear regression works. It would have a linear relationship with respect to the target variable. So in this case, what we need to do is we need to identify if I have a prediction somewhere on this graph, then I need to also know that what is my target value was for that particular prediction. And if I observe that my target had some difference with respect to the prediction, then I need to take a difference of that. Why? That is because that is giving us the error between the target and the prediction. We're gonna go through one of the sample exercises in the upcoming slides. So let me take you to the next slide. How do we find the most appropriate value of m and b? Well, that's a good question. Okay, so the value of m and b is going to be appropriate based on an error. So let's first understand what do you mean by the loss function and how do we compute the loss function. Okay, so we can measure the accuracy or the goodness of a linear regression model by finding the error difference between the predicted output and the actual output, and that's what I was trying to illustrate. So basically, anytime you have a prediction, you subtract it from the actual output and you do the square of that and divide by number of observation. That should give you mean squared error. Okay, so why we are doing it? Okay, so let's take this particular picture into the account where we are seeing different dots coming up below the line and above the line, and the whole idea is to find the fit for the line, right? How do we find it? Let's say we have a given sample of data points, and let's try to fit a line that shows a linear relationship for target variable. So the best way to find the fit of the line is to keep finding the loss distance with respect to the target as the minimum of mean squared error. So if I take 10 data points over here and if I get my mean squared error as some value and I find an intercept for that and I find the weight for that, and if I see in totality my mean squared error is lowest for that particular regression, then that should be my slope, then that should be my weight and bias. But in case it's higher, then I need to further keep performing regression so that I can find that particular fit of the line that gives me the lowest value of the mean squared error. That's the whole objective of evaluating the predictions based on the linear regression model. Okay, so in this case, I've already covered in my one of the examples how to compute the prediction for linear regression. But let's consider this snippet. Imagine you already have a data frame where you have target, obviously, and you have done the predictions for that. So how do you calculate the residual? You basically take the difference of target and the prediction. And then in terms of the difference percentages, all you have to take is the absolute difference, which is obviously from the previous step residual, which we have calculated, divided by the target and multiplied by 100. That should give you the percentage of the differences. And since we discussed about the loss function is nothing but mean squared error, which is basically calculated by taking a difference of, again, the target and the prediction, doing the squared of that and dividing by the total number of observations. And that's what exactly we're doing. NP dot square, taking the target from the data frame and subtracting the prediction from that particular target, dividing by total number of observation, which is computed as length of the data frame of the target column, and that should give us the total number of observations. And now let's see our tally. If I see this tally, I can see the very first row giving me prediction of 9.939, target as 9.94, residual is 0.007, difference is 0.07%, and obviously loss is coming around 0.00059. So likewise, this is a particular prediction coming out based on a linear regression, which gives us the least mean squared error. So obviously, when we are running the factory method of linear regression model, it does a couple of regressions to compute the minimum mean squared error, and whichever gives the lowest value of the mean squared error, those are your intercept values for B. We call it the bias, or also the slope, and that's how you account for the loss function for computing the loss in a linear regression model and taking the accuracy of the model to a higher value based on your mean squared error. Okay, I hope you fundamentally understood the concept, and we're obviously going to be discussing the details about computations in our exercise. And thanks for joining the lecture. I'll see you next in the next lecture. Hello friends, welcome to this lecture. In this lecture, we'll be implementing the linear regression model. So some of the steps for our linear regression model are, we're going to be importing the data set, then we'll find the outliers. That being said, if there are certain attributes which demonstrate anomaly, and then we want to make the corrections and then basically be able to clean our data set. Then followed by that, we would be visualizing our data. Since we are leveraging the renters data, and all we have to do is make the predictions for the rents by a city, then we need to be able to see and make the comparisons of different rents by the number of the bedrooms, number of the baths, and yeah, and other major key decision data points that would drive the rent of a particular bedroom. Then we would be filtering our data set. After the filtration of our data set is done, we would be encoding the categorical data, and we are employing the label encoding technique over here. Then eventually, before we pump our data into our model, we need to do the scaling of our data. In this case, we are using min-max scaler. You can use other scaling techniques as well. Then as part of the model building pipeline, we're going to go ahead and train test the model, then implement the linear regression model. Finally, we would be making the predictions. And once the predictions are ready, we should be able to validate our root mean squared error and mean squared errors. And also, I would recommend doing the exercise of visualizing the losses, and finally tabulate the predictions versus the actuals. So you can see how your predicted data set behaves with respect to the actuals. So let's go ahead and import these packages. So we need the package for matplotlib, seaborn. Let's go ahead that. Also import the pandas and numpy packages. Then you would be importing the package like train test split from sklearn.model selection, and also import the package for linear regression. And as I mentioned, for label encoding, go ahead and import the label encoder as well as min-max scaler. You can also import other packages if you want to train your data through different scaling techniques. Finally, in order to validate the model, you can import from sklearn.metrics mean absolute error and mean squared error, and also the R2 score. Now what I'm doing is, in the next cell, I'm gonna use my dataset that's house rent dataset. Let's do pd.read.csv. I'm basically storing the data in my data frame called renDF. Once I press the command rendf.head, I can visualize, basically be able to tabulate this data, and it has the first column being the date posted on, the number of bedrooms, it has the rent, the size, the floor, area type. Likewise, we have a bunch of other columns followed by tenants preferred and point of contact. Also note that we have furnishing status. So in this data set, we would be basically excluding unfurnished data set and be able to make the predictions on semi-furnished and the furnished one. So now that we have done that, let's visualize the number of the rows and columns. So if we do rentdf.shape, we have roughly around 12 columns and 4,746 rows. So that's the structure of our data set. Now also we can do df.info. If we do that, we can see the data types for our columns, right? So some of the columns are like rent, size are integer, rest of them are categorical, and also the bathroom is integer. Since those columns which are categorical, we will need to do some encoding. That means we would convert them into a value which is um, like an integer value, so that we can pass these column values as a distinct values for our model to be able to apply the linear regression regressor. All right, so now that we have done this, the next is we're going to find the outliers over here. And let's come back in the next lecture. We would review the exercise of finding the outliers and be able to remove the anomaly. Thanks for joining. What we're going to do is we're going to find the outliers in our data frame. And for that, what we're going to do is basically creating a function called def find outlier. And in order to find outliers, we're going to find the upper threshold and lower threshold. So what I'm doing in line 3 and 4, I'm defining these thresholds. So imagine if any column is there, and I take the mean value and then apply a factor of standard deviation. That will give me upper threshold. In this case, the factor is twice the standard deviation, and in the lower threshold, we're going to take the mean value and subtract it from the standard deviation by a factor of 2. So this gives the upper bounds and lower bounds, and then we're going to apply this across all columns. So we're going to use the for loop for var in columns, or you can say column list. And then if var is less than the threshold or var is greater than threshold, that implies we have an outlier. So we're setting count is equal to 1, else count is equal to 0. That means they're an outlier. And then setting the value of the flag, outlier flag is equal to count, whichever. If it's an outlier, yes, the value is going to be 1. Otherwise, the value returned is 0. Finally, we are returning a series, and we are applying on the series some functions like the first value. If we see n is basically how number of observations we have. Do we have any null values and miss, followed by sum, mean, median, and standard deviation. Solve them for we want the quantile function. That means what is the property distribution function for 50% versus 99th percentile. So likewise, and finally we are publishing the values of our lower threshold and upper threshold followed by the flag. So that's our outlier calculations, and we would be implementing it. So first, go ahead and let's find out the categorical, or basically our numerical columns. So I'm creating a list over here basically, and I'm running this list with the for loop in my data frame, which is rendf. And if I say if data type is integer, then I'm going to append this list, and basically I can find, then this is my integer list. My bedroom is going to be 1 2 3 4 5. Rent is going to be some amounts. Size is also going to be like the amount, as well as the bathrooms is going to be a numerical number. Now we have done that, and let's go ahead and apply the outlier function. So over here what I'm doing is on my data frame, for all the numerical columns I want to apply the outlier function. So I'm going to publish in the list numerical columns that we have computed above, um, and yeah, and what I'm going to do is basically apply the lambda function for the outliers, where if I run this cell, basically I should be able to see all these observations. So for all these columns, which is uh, the bedroom, rent, size, and bathroom, I can see the number of observations, number of records missing, sum, total, median, and then the probability distributions. You know. So now that we have done this, the next thing is we're going to start visualizing our data. So stay tuned for the next lecture. Thanks for joining. We're going to visualize our data set. So in the next cell, basically, what I'm doing is I'm doing plt.figure. I'm defining the figure size. And let's do the box plot for our data. So I'm also applying my data frame, rentdf, and I want to see the rent values, the box plot. And we can see certainly there are some outliers. Anything above 200,000 we won't exclude, because we don't want to bring that data for training a model. Then what I'm doing is I am basically creating a filter for all the values less than 200,000, and that's what we want to have our filtered data set. Let's do this filtration. Once this is done, let's go ahead and visualize our box plot again. And if you see this box plot, I can see all the values less than 200,000, and yeah, and there are values roughly, mostly the median range around 25,000, and some values exceeding 50,000, and likewise up to 200,000. Right, so those dots represents some outliers values over here, and what we're going to do is we're going to do another bar plot by city. So in this case, we would supply a data frame and set the x value is equal to city and y is equal to rent. So now we can see rent by each city. So we see the city 2, which is Mumbai, has the highest rent, followed by the second city, which is Delhi, followed by Bangalore, which is aligned with the fourth city, which is Chennai and Hyderabad. Seems to be pretty similar numbers. That's fine. And let's do the value count for the next one. So if we do by area, do the value count. Here is super area 2436, carpet area 2200, and built area is also a number over here. Now what we're going to do is we're going to do another part. This one bar plot is for x-axis equal to city, and we want to plot the rent, and we want to introduce a notion of hue by area type. So now that we know that the area type could be super area or carpet area and built up area, now we can see that the blue line, basically an orange line, indicating that if the super area is involved, again Mumbai is leading, and if the carpet area is involved, again Mumbai is much expensive, followed by Delhi. All right, now let's go ahead and another visualization, again a bar plot. Again we're going to add the hue over here, furnishing status. If I furnish the same apartment, how much it makes a difference. So I can see that green one indicating the rent still exceeds 70,000. If it's semi-furnished, the rent would be somewhere around 70,000. If it's unfurnished unit, it just drops the rent by 40,000. Guys, putting the furnishing item may not be that expensive, so that gives an indication that the renters who are putting the property must furnish the property in order to maximize the rents. And likewise, the trend, we can see similar trend of furnished, unfurnished in other cities as well. Now let's do another bar plot. In this case, we're adding hue is equal to BHK, number of bedrooms. If we add more bedrooms, it indicates that Delhi is the leader in terms of getting the value for the rent. It's much worth, and Mumbai falls second, and then we have trailing numbers for other cities. Let's do another visualization. In this case, we are just checking for number of bedrooms is equal to 6, and if we do that, let's visualize our plot, and we are adding the tenant preferred over here. And again, Mumbai is the leading one. If we look at the split by bachelors versus family and family, basically between family and bachelor's family, if it's a combo, the rents are high, while for bachelors the rent's going to drop. And other cities quite significantly, that's half the median rent, so there's a huge difference between the city 1 and city 2 and 3. Alright, so now that we have done that, what we're going to be doing is we again do the value counts for the bathroom, and let's visualize the results for the bathroom. Over here, I'm doing the bar plot, and let's set the hue as bathroom. And yeah, Mumbai again is leading in the rent. And if the number of bathrooms are somewhere around 6, your rent could be much higher. And if you drop the number of bathrooms, let's say 1, that can be like 1/5 the rent or 1/6 the rent over here. That's a quite drop. And if I have to consider optimal value, somewhere between 3 and 4 would be an optimal if you want to optimize your rent. So yes, so carpet area, super area, furnished, and the number of bedrooms as well as the bathroom concede to the amount of rent one must be paying by city. Alright, so we have done this. We have done the value counts of bathroom. Let's do one more plot over here, and we're gonna add hue as a number of the BHK. Is it 1 bedroom, 2 bedroom, 3 bedroom, 4 bedroom, and we can see again the more you add the number of bedrooms, the type of the BHK it is a 4 BHK, 3 BHK, it would be a driving factor for your rent. Alright friends, so now that we have visualized these results, what we should do is we should come back and start playing with our data, where we would be doing next exercise about filtering our data sets, scaling our data set, and then be applying machine learning models before we do the predictions. So stay tuned for more lectures. Thanks for joining. I'm going to see you in the next lecture. Now is the time to go ahead and filter our data. So I'm going to come back over here. Before I filter, let's sort the value of our data frame, and I'm doing sort by rent. Now if supply that, we can see that our rent is now in ascending order. So that being said, the records showing the rent with 200,000 on top, followed by the lowest on the bottom. Now that we have that, and we can also see the distribution for our rent. If I say df rent equal to 200,000 dot value counts. That's a distribution. Now let's create a function called filter data and supply our data frame over here and df. And if I want to filter the data for all the records which are less than 150,000, let's do that, and also set the furnishing status is equal to unfurnished. We have that filtered data frame rendf, and also remove any numerical values with negative values. For that, we're gonna supply a filter again where rendf all for all the numerical columns value less than 0. On the x-axis we want to eliminate them, and then also we want to drop the column. So for that, let's prepare a list called drop call, and we are defining posted on floor area locality point of contact, and let's do df.drop and supply columns is equal to drop and in place is equal to true. If these columns exist, they must be eliminated. And finally, we would also filter on the built up area. So where I'm saying rand df and df column which is area type not equal to built up area or built area, I am able to shortlist my data frame. Now that we have done this, we have to do the encoding after this. So let's do that. So over here, I've called the filter data frame and stored the result in rendif. If I run this, you can see these observable value sets over here. I need not to go over here, but just to give you a illustrative view of what sits in our filter data sets, we are left with 8 columns and 4,622 rows. Now I'm basically encoding the data. So we have numerical as well as categorical values. So some of the categorical values belongs to a column like city, area type, furnishing, status, and tenant preferred. So for that, let me explain these few lines. What I'm doing is I'm taking the as type as a category for the column city. Once I have that, I will put all those supplied values, the unique values for this city into categorical object all cat, and then I'm calling the label encoder, which basically encodes a value. Let's say if I have a value of gender, which is male and female, it will encode as male as 0 and female as 1. So this label encoding would work perfectly for us to be able to convert all categorical feature sets into numerical. So once we have that, we're going to fit our values, which is categorical values all cat. We'll supply encoder dot fit all cat, and then finally store the values, the encoded values, back into a column called rendf. If I do encoder.transform rendf city, this would now transform the values into categorical to numerical values, right? So these are basically would be converted as all the numerical values. A set of values could be 1 2 3 4, something of that genre. So once we have done that, we're going to do the same exercise for the column called area type. We're going to do for furnishing status, tenant preferred. Once we have done that, return the data frame and basically call the encode data. So I'm going to come in the next cell. I'm calling encode data and then a supplier rent df, which is a filter data frame, and store the results. And that's it. We are done. Let's go ahead and visualize the results. In terms of this table, we can see all these columns now have numerical values supplied. None of the column has any categorical values, and now it seems our data is good, but we still need to scale our data because columns like size is something we need to really take care of, because rent is going to be our target feature. We do not do any scaling, but the size is basically something we will have to tweak it. So we probably be using min max scaler and go ahead and resize our column so that we can supply the right scale values into our data frame. All right, friends, hope you're enjoying these lectures. Stay tuned for more lectures. Thanks for joining. So in the last lecture, we have done the encoding of the data. So let's call the function encode data, pass the data frame, and store the results back into our rent data frame. Let's go ahead and run this rent data frame, and we can see all the features encoded except the size. And the size, we need to do the scaling. Let's go ahead and implement the scaling of our column. So I'm in the next cell, I'm creating a function called scale data, passing in the constructor rendf. Let's call the function called min max scaler, create the instance of it in scalar object. Then we're going to do fit transformation by calling scalar.fit transform, and I'm going to pass my data frame column, which is the size, and I'm going to reshape it -1 comma 1. Finally, I'm going to store the value of the scaled values into a new column called size scaled. And once we have done this, we don't need any more the size, so we should df.drop the column name, which is size. And finally, we're going to do the parameter assignment for x and y. For that, we need x is equal to by data frame dot drop all the columns except, sorry, so I'm going to do rent df dot drop, and I'm only going to drop the rent over here, and rest we need the features. For the target, we're just going to take the column from the data frame rent, and we are done. Finally, return xy and rent df. Now is the time to go ahead and invoke the instance of scale data, and we have now x and y in RenDF. Let's go ahead and visualize the results of RenDF. So if we tabulate the results over here, we can see, okay, so before I even tabulate that, what we're going to do is we're going to train split the data. So I'm calling the factory method from the sklearn, which is train test split, specifying x and y, and then I'm also specifying the test size as 20%. Random state is best random state, it's parameterized. That way we have x train, x test, y train, y test. Finally, now we can run the x train. In this cell, we can observe we have 7 columns and 3697 rows. So we are good to go ahead and train our model against the linear regression. So I'm going to create the instance of linear regression now. And then to that model, I'm going to fit x train and y train. My training and target features are trained now. Once they are trained, all I have to do is make the prediction. So let's go ahead and make the prediction. So I'm going to call model.predict and pass a test feature. So that should give us all the predictions over here. So once the predictions are ready, it's now time to use sklearn.metrics to evaluate a root mean squared error and mean squared error and R2 score. So in the next one, I'm using a bunch of factory methods, which are mean squared error, mean absolute error, R2 score. All of them take in the argument in this constructor the actual versus predicted. So over here we're going to give y test, y pred, same thing for mean absolute error, and similarly for R2 square. Finally, the root mean squared error is square root of the mean squared error. So we're going to use a math operator dot to square root. That way we got that values. Then if you are interested in calculating adjusted R2 score, then we need these values, and those values are basically n is the length of our test feature, p is actually the size of our columns, which is 7. Then adjusted R2 square is expressed as 1 minus bracket 1 minus R2 square times n minus 1 divided by n minus p minus 1, where the values of n and p are defined above. And if we print these values, we can observe, if I run this up, observation states that our mean squared error is quite high, root mean squared error is also quite high, and R2 score is 50%, which means typically the acceptable rate for R2 square is more than 80%. So the area under the curve that is acceptable for linear regression. So what we're going to do is we should be able to compare using the cross validation uh, XGBoost regressor or support vector model or Lazo model. It's up to you. I'm going to use one model to be able to see whether we can see a lower mean squared error by doing the cross validation using the different model on the same training features. All right, so that should be our next exercise. So stay tuned. Before I wrap up the lecture, we'll also be covering other aspects over here. Once we have tabulated our predictions, we should be able to compute our residuals and be able to tabulate those residuals, and then finally create the table for actual versus predicted, so we know that how well we have scored in terms of making the predictions on our actual data set. Alright friends, I hope you guys enjoying. Stay tuned for my lectures. Thanks for joining. So that our mean squared error is quite high. Let's be able to compare with another model. So for that, I'm going to perform the cross validation. In the next set, if you can see, I have created models as a dictionary, and I'm passing linear regression as well as gradient boosting, and we're specifying a specific class for linear regression and gradient boosting regressor. Over here, I'm iterating the model name and model for model.items. And I'm calling the factory method crossval score, where the constructor takes the arguments as model and the training features, which is x train, y train, and I'm specifying number of cross validation folds as 5, and it's also specifying the scoring for the mean squared error. Then basically we would be computing our RMSE, mean and standard RMSE. The first one is a root mean squared, which is a square root of the scores, and we will apply a numpy dot square root of the minus score. That way we got the root mean squared scores. Then we would take the mean value by applying a mean function. That way we have mean RSME. Then in order to get the standard deviation, then we will just simply go ahead and apply the standard deviation. finally, we'll print these scores. And you can see that the linear regression is having a higher RMSE compared to the gradient boosting. Now, since the objective is to use linear regression, we'll continue to use linear regression, but in ideal world, you will do an ensemble approach and be able to use a model which gives a higher efficacy. Thanks for joining. So what we're going to do is we're going to take the actual values, the test minus the predicted, that's our residuals. Let's go ahead and create a dictionary. So I'm creating a dictionary called data is equal to my label predicted is ypred and residuals is actual, the difference of the actual versus predicted. Finally, convert into a data frame. So I'm going to apply pd.dataframe and pass my dictionary over there. So that way we have the residuals stored in the dictionary now. The next is I want to visualize this plot. So the way I'm going to do is I'm going to use a histogram or a hisplot basically. So I'm going to use cbond sns.hisplot, pass the residuals, and the KD type is true. And of course we're going to set the titles, and if you see that the distribution is tends towards mean tends towards 0, and we can see the negative values are basically on both the sides offsetting beyond 50,000 and minus 50,000, so that's a good residual. And now the next thing is we're going to go ahead and plot the scatter plot. So we're going to plot the scatter plot for prediction versus residuals. So let's go ahead and do that. Let's specify the figure, plt.figure, set the figure size as 12,6. Do the scatter plot by plt.scatter, use the first target variable, which is ypred over here, and the residuals because we are plotting it. And also we're going to create a horizontal straight line. So for which we're going to use plt.ex line. On the x-axis, we want to create a horizontal line. So let's set the color is equal to red. Set the line style as this icon. Finally, set the title as a residual plot and set the x label and y label. X label is predicted values and y label is residuals. Finally, to do the plot, let's do plt.show, and here are observations. We see that we have a horizontal line which is red color. These are the residuals. The observation is the more our predictions are towards the higher values, the residuals are more sparse. That means we are not able to get the right prediction. That's why residuals, we are having higher variance in the residuals. Okay, so the next is basically over here, we are doing a QQ plot. QQ plot stands for quantile quantile, in short called as QQ plot. In simple terms, it's a method to compare the two distributions, and in more formal term, it is a technique to compare whether two sets of sample points are from the same distribution. Now, simple, we are doing the QQ plot for only for residuals, so we're going to call stats.prob plot and pass the residuals, call the distribution norm, and plot is equal to pylab. Set the title as QQ and do pylab.show. If we do that, you can see that we are observing that there is a straight line for the quantile distribution of the residuals. So that's pretty much indicative that this distribution is quite uniform, but then it tends to have some anomaly in the distribution for the residuals, because as we saw that higher our predicted values are for the higher end, we have higher residuals. So that's basically our distribution for the QQ plot. The next is basically we're going to be doing the predictions for um, we're going to be plotting the predictions. For that, we're creating a function called def plot predictions. We need to argument the actual versus predicted. So we're going to assign the actual values from ytest, predicted values from ypred, and let's set the figure, which is 10,6. Let's do the scatter plot using cbond sns.scatterplot. Actuals is x and y values. So x is actual values, y is predicted values. Set the label title. Label is basically actual value for the rent. Y label is predicted values. And finally, we have a title for actual versus predicted. And then basically do the plt.show. And if I call this function plot predictions by passing both the arguments of actual versus predicted, here are observations. So we can see that we have a straight line for the predicted values, um, which is indicative of our linear regression model, and any value that doesn't match, the difference of that would be our root mean squared error. And yeah, any difference over here, the actual versus predicted is our the error. Uh, so and that we calculate through root mean squared error as we have done the previous calculations. So yes, our prediction values are much better off if they are in line between the values anywhere from the lowest bound to be, maybe I can say 50,000 or somewhere between 75,000. The more the higher the rent, we are not able to make accurate predictions, and we have higher error, or higher, or the residuals going to be much higher. So those are our observations for our predictions. The next is we're going to go ahead and tabulate the results. So stay tuned for the next lecture. Thanks for joining. In the previous lecture, we were able to plot our predictions. We saw there is a linear line that represents our predicted values, and we saw there is quite a difference in the residuals values as we compare actual versus the predicted values. As our the rent price increases, our predictions are less accurate. And also, as a quick recap, what we have done in the previous lecture was QQ plot. Then also we did another residual plot, and also we were able to plot the residuals as a histoplot. Now that we have done this, we only left with tabulating our actual versus predicted. So that's very simple exercise, friends. So we're gonna go ahead and create a new data frame. So I'm creating a data frame called actual and predicted columns, where the actual value is the y-test and the predicted is y-pred. And then let's call pd.dataframe, store the results in a data frame called results. And then you want to round the results and then store the actual output into the same data frame results. Finally, we can run this cell, and here are our observations, here are the actual values, and here are the predicted values. So obviously our numbers are not in line with the higher accuracy because the prediction R2 score was around 50%, and this is definitely just a mock exercise for us to learn the linear regression. I recommend, as you learn through other different machine learning models, be able to compare and optimize your accuracies across different models and use a model which gives us the highest accuracy. All right, friends, I hope you guys keep enjoying the lectures. Stay tuned for more lectures. Thanks for joining.